Chapter 7 is on chemical bonding and molecular geometry. The first section of this chapter is on ionic bonding, and it should be pretty much a review of what you've already done in chemistry with ionic bonding. By the end of this section, you should be able to explain the formation of cations, anions, and ionic compounds, and predict the charges of common metallic and nonmetallic elements, and write their electron configurations. So first of all, ions are an atom that has gained or lost electrons. And there are two different types of ions: anions, which have a negative charge, and that negative charge is formed by gaining electrons. And cations are ions with a positive charge, and that positive charge is formed by losing electrons. Anions tend to form from nonmetals, because nonmetals want to get up to 8 valence electrons, and it's easier to gain the couple that they're missing than to lose those that they have, because nonmetals tend to have more than 4 valence electrons, whereas metals have 4 or less valence electrons, so it's easier for them to lose their valence electrons than to gain enough to get up to 8. Ionic bonds are just caused by the positive and negative attraction of the ions once they've formed. Ionic compounds have a crystalline structure, so a regular repeating pattern of the ions. They tend to be very brittle, have very high melting and boiling points, and as a solid are very poor conductors. They won't conduct electricity in solid form, but if they are melted or dissolved in water, then they will conduct electricity because their ions are free to flow. And many ionic compounds will dissolve in water. We talked earlier about the solubility rules, and we know that there are some ions that don't dissolve in water. The ions that make up an ionic compound, again, have very different properties than the atoms that make them up because their electronic structure is very different. A binary ionic compound, the prefix bi means 2. So a binary ionic compound is one that's made of only 2 elements. One would be a metal, which forms the positively charged cation, and the other would be the nonmetal that forms the negatively charged anion. Metals have very low ionization energies, which is why they lose electrons so easily. Nonmetals have high electron affinities, therefore they gain those electrons easily. We need to remember that while the ions themselves are charged, the compounds overall are neutral, so we need enough positive ions and negative ions, the correct ratio, to balance out and make sure that that compound overall is neutral. Also, it is not a molecule. A molecule would indicate that 2 specific ions are linked together, but they're not. The attractive forces between any sodium ion and sodium chloride is equal to all of the attraction, or is equally attracted to all of the chlorine ions that are next to it. It's not more attracted to one than the other. And those attractive forces are very, very strong, which is what makes it a solid. When main group elements, that's things in groups 1, 2, and 3, or 13 through 18, when the main group metals form ions, they tend to lose all of their valence electrons. So everything in the S and P sublevels are lost, and they become isoelectronic, which means they have the same electron configuration as the noble gas directly before it. So things in group 1, their valence electrons are in the something S1, they'll lose that 1 valence electron. In group 2, we'll lose both that filled up the S sublevel, etc. Things that are in groups 12 through 17 have a full D sublevel. So the group number is greater than 10, or is 10 greater than the valence electrons. So things in group 13 tend to lose 3, the 2 in the S, and then that 1 in the P sublevel as well. Toward the bottom, there are weird exceptions in terms of what ions things will form. So essentially, that's because the paired S electrons change things and weird things happen. The transition metals, remember, they can often form multiple charges. So we know that when we fill the valence electron, or when we fill the electron configuration, the S sublevel is filled first and then the D sublevel. However, when they form ions, they tend to lose those S electrons first, even though those have a lower energy, and really weird reason for why, but they will lose the S electrons, which are their actual valence electrons, first, and then they will also sometimes lose some of the electrons from their D sublevel as well, which is why they have such weird multiple charges that are possible. All right, so here we want to write the electron configurations for the chromium +3 and the zinc +2 ions. If we look at chromium, chromium is atomic number 24. So the noble gas right before that is argon. So we can do if I can find it, I can write it out. So the noble gas directly before the chromium ion is argon, so we can do the abbreviated electron configuration and say it has everything up to argon. And then if we look at it, the chromium +3, there are 24 electrons in chromium, so 24 +3 ion would have 21 ions. The chromium atom, and I'm going to write this out without superscripts and try and use spaces just because I'm typing, would be 4s2, 5d, sorry, not 5d, 3d, 4. When it forms the +3 ion, it loses those S electrons first, so we lose 2 from the S and then another 1 from the D, so it's 3D with the superscript of 3. Zinc +2, so if I do another, can't get another box. All right, so for zinc, zinc is in that same group, so it would be argon as the noble gas directly before it, and then zinc has 30 electrons, so it would be 4s2, 3d, and that d sublevel is filled, so 3d10. When it forms that +2 charge, it's the S electrons that are lost first, so it would be argon 3d10 as that electron configuration. Non-metal atoms will gain enough electrons to completely fill their outer s and p orbitals, always. So these will be a little bit easier. If we want to write the electron configurations for a selenium ion, so selenium is atomic number 34. So again, the noble gas right before it is argon. And then the selenium atom would also have the 4s2, followed by the 3d10, and then 4p, and the atom is 4p4. But it's going to fill up that p sublevel, so it would be 4p, the p sublevel can hold 6. All right, the iodine ion. Iodine is 53. If we look at the noble gas right before it, its noble gas preceding it is krypton. So we're going to have krypton followed by, we're now in 1, 2, 3, 4, period 5. So 5s2, 4d10, and then 5p. Iodine would be 5p7. The iodine ion would gain enough to fill, or sorry, 5p5. The iodine ion would gain enough to fill that p sublevel, and it would be 5p6. So when we're writing electron configurations, we first need to determine whether the element is a metal or a nonmetal. The metals are going to lose their valence electrons. If it is a transition metal, they're going to lose from the S sublevel first and then a couple from the D sublevel. If it's a main group element, then it will just lose all of its valence electrons. If it's a nonmetal, then it's going to gain enough electrons to completely fill that outer S and P sublevel. The S will always be filled already, and then you just need to get the P sublevel up to 6 electrons.